Have you ever wondered why some computer programs run faster than others, even when they're doing the same task? Well, the secret sauce behind this speed difference is the efficiency of the algorithms at the heart of these programs. Algorithms are like the brain of a computer program, dictating how it should process information and solve problems. Just as human brains differ in how quickly and efficiently they can solve a puzzle, algorithms too vary in their efficiency. The speed and performance of a program are directly tied to the efficiency of the algorithms it employs. Think of algorithms like different routes to a destination. Some routes are faster but might require more fuel, while others are slower but more fuel efficient. Similarly, some algorithms are faster but demand more computational resources, while others are slower but use fewer resources. The trick, therefore, is to find that sweet spot in algorithm that gets the job done quickly without guzzling computational resources. But why does algorithm efficiency matter so much? Well, in today's digital age, where users demand instantaneous responses and businesses require real-time data processing, the efficiency of algorithms is paramount. Every millisecond counts. Efficient algorithms allow programs to process larger amounts of data more quickly, leading to faster and more responsive software. In addition, as we move towards handling larger and more complex datasets, it becomes increasingly important to have algorithms that can scale effectively. An algorithm that works well for a small dataset may not perform as efficiently when the data size increases by 10-fold or 100-fold. Efficient algorithms are those that can handle such scalability, ensuring that as the data size grows, the algorithm's performance doesn't deteriorate drastically. And let's not forget the cost factor. More efficient algorithms equate to less computational power, which means lower infrastructure costs. So, it's not just about speed and performance, it's also about cost effectiveness. So, how do we measure the efficiency of an algorithm? That's where big O notation comes in. Big O notation might sound intimidating, but it's actually a simple concept once you break it down. Think of it as a way to measure how fast an algorithm runs as the size of its input grows. It's a bit like a speedometer for code, giving us an idea of how quickly our algorithm will complete its task as we feed it more and more data. Imagine you're cooking a meal. If you're making a single serving, it might take you 30 minutes. But what if you suddenly have to cook for 10 people, or 100? Your cooking time will increase, right? This is similar to how an algorithm works. The more data it has to process, the longer it will take to complete. Big O notation helps us predict this growth in execution time. It gives us an upper bound or a worst-case scenario of an algorithm's performance. This doesn't necessarily mean the exact time it will take, but rather the rate at which the time increases as the input size grows. For example, if an algorithm has a big O notation of ON, it means that if you double the input size, the execution time will also roughly double. If it's ON squared, the execution time will quadruple, and so on. However, big O notation isn't just about time. It can also be used to measure the space an algorithm uses. This is crucial because in computing, resources are finite. We have to be mindful of how much memory our algorithms are gobbling up. What makes big O notation so useful is its focus on the long run. It's all about what happens as the input size approaches infinity. It lets us ignore small details and focus on the big picture. This means we can compare different algorithms and make informed decisions about which one to use, based on their efficiency and scalability. Now that we understand what big O notation is, let's explore some common types of big O notation. The beauty of big O notation is that it's not just a single measure, but a range of measures. Let's delve into some of the common types of big O notation. First up, we have O1, also known as constant time. This is the ideal scenario where the execution time of an algorithm remains constant, no matter how large the input size gets. It's like having a magical book that opens directly to the page you want, regardless of how thick the book is. Next, we have O log n, or logarithmic time. Here, the execution time increases logarithmically with the input size. Imagine trying to find a word in a dictionary. You don't go through each page one by one. Instead, you divide the dictionary into halves repeatedly until you find the word. That's logarithmic time for you. Moving on, we have ON, or linear time. In this case, the execution time increases directly in proportion to the input size. It's like reading a book from start to finish. The more pages there are, the longer it takes. Then we have O and log n, also known as linearithmic time. This is a common time complexity for efficient sorting algorithms. It's a bit like organizing a library of books. You'd first sort them, that's the n part, then shelve them in order, that's the log n part. Next in line is O(n squared, an example of polynomial time. The execution time here grows square to the input size. This is like trying on every pair of socks in your drawer to find a matching pair. Lastly, we have O, 2 circumflex n, an example of exponential time. Here, the execution time doubles with every additional input. It's like a game of chess where the number of possible moves explodes exponentially. These are just some of the common types of big O notation. There are many more, each representing a different rate of growth. By understanding these notations, we can better analyze and compare algorithms and make more informed decisions when designing our software solutions. You might be thinking, this is all well and good, but why should I care about big O notation? Well, the answer lies in its real-world applications. Big O notation isn't just a theoretical concept confined to textbooks. It plays a crucial role in the practical world of software development and algorithm design. Imagine you're a developer tasked with creating a sorting algorithm for a data set. You have a plethora of algorithms at your disposal, each with its own strengths and weaknesses. How do you decide which one to use? This is where big O notation comes in. It gives you a standardized measure to compare the efficiency of different algorithms. Let's take an example. If you have a sorting algorithm with a time complexity of O(n squared, it means the algorithm's execution time increases quadratically with the size of the input. If your dataset doubles, the execution time quadruples. Now, if you're dealing with a small number of inputs, this may not be an issue. But what if your dataset spans millions of entries? Suddenly, your algorithm becomes a bottleneck, slowing down your entire application. By understanding big O notation, you can anticipate these issues and choose algorithms that scale well with increasing input size. This is especially important in today's world, where applications often have to process massive amounts of data. But that's not all. Big O notation doesn't just help in choosing the right algorithm, it also aids in improving existing ones. By analyzing an algorithm's time or space complexity, you can identify inefficiencies and potential areas of optimization. Perhaps you can reduce the number of operations, or maybe you can find a way to use memory more efficiently. In essence, big O notation helps you make informed decisions about algorithm selection, optimization, and performance tuning. It's a tool that allows you to create software that's not just functional, but also efficient and scalable. So, understanding big O notation is not just about theory, it's about making your software faster and more efficient. Let's take a moment to revisit what we've learned today. We've delved into the realm of big O notation, a mathematical notation that's not just a symbol, but a language that communicates the efficiency of algorithms. It's the worst-case scenario, the upper bound of time or space complexity, that we're talking about when we use this notation. Think of big O notation as a yardstick, a measure of how an algorithm behaves as the input size scales up. It's all about the growth rate and how swiftly the time or space requirements of an algorithm increase with the input size. It's like a speedometer for your algorithm, telling you how fast it's going to consume resources as the journey gets longer. We've also explored the different faces of big O, from the constant time O, 1, where execution time remains steady, to the logarithmic time O log n, that increases at a decreasing rate. We've seen the linear time O(n), where time and size move in tandem, and the linearithmic time O(n log n), that's a common sight in efficient sorting and searching algorithms. We've not forgotten the polynomial time complexities O(n squared, O(n cubed, and so on, where execution time goes up polynomially with the input size, nor the exponential complexities O, 2 circumflex n, O(n), where time shoots up dramatically with increasing size. But why does this matter? Because big O notation is not just a concept, it's a tool. It helps us choose the most fitting algorithm for our needs, based on its scalability and performance characteristics. It guides us in scrutinizing algorithms, understanding their behavior, and optimizing them for efficiency. Take a sorting algorithm with a time complexity of O(n squared, for instance. Knowing that the execution time quadruples as the input size doubles helps us make informed decisions about when to use this algorithm and when to look for a more efficient alternative. Remember, understanding big O notation is a crucial step in becoming a proficient software developer. So keep practicing and keep learning. Until next time, happy coding!